All right, next we've got example 5. Water pours into a conical tank of height 10 meters and radius 4 meters at a rate of 6 cubic meters a minute. So let's go ahead and first just draw a conical tank. So here's a cone. And then we know that the height of the tank is 10 meters. And we know that the radius of this tank is 4 meters. We know that water is flowing in at a rate of 6 cubic meters every minute. Because we know that the volume is increasing by this amount, we know that dV dt, the rate of change of volume with respect to time, has to be positive 6 cubic meters per minute. All right, so as this process is ongoing, if we just imagine freezing a moment of time, at any given moment in time, the water is going to occupy some amount. So let's say this portion here is filled with water. Well, at that moment, there is a certain radius, right? We can actually kind of freeze time here. Let's just draw something right down the middle here. And at any moment in time, there's going to be a certain height of water. Let's call this distance right here h meters. And we'll call this radius for the cross-sectional circle, because we can think of a little cross-sectional circle, and that would be r. So the tank has radius 4 and height 10, but as time goes on and as water fills this tank, then h is going to increase, and so is the radius. Okay. So let's go ahead and actually try to come up with a formula for the volume of this little cone of water at the bottom. So the volume of a cone is 1/3 pi r squared times the height. Now that we have that, ultimately, what are we asked for? We are asked in this part A, at what rate is the water level rising? So the water level would be the height. So our goal here is actually to figure out dH dt when the water level h is exactly 5 meters. So we know what dV dt is. We know what dV dt is. That's 6, and this is the rate. So we come up with this equation, the volume, because we know information about the volume, and this just so happens to involve information about the height. So we have successfully obtained a relationship relating v and h. So now we can go ahead and differentiate. Now there's a little thing here that is very useful for these kinds of problems, and that is, right now we have v expressed in terms of pi and 1/3 are constants, so this is just a constant. But these two things are not constants, they're changing. As water fills the tank, both the height will increase and the radius of that cross-sectional circle will also increase. So we actually have a product of two functions, r squared and h. So if we were to differentiate this, we would have to do a product rule here, which is fine, but we're working a little bit harder than we need to. So instead, it would be better to try to eliminate one of these two variables. Since we're given information about h, we want to know specifically this rate when the height is exactly 5. We probably don't want to get rid of h because we're going to have to use the fact that h is 5 at some point. Let's try to eliminate r. Well, in order to eliminate r, we need to somehow come up with a relationship between r and h. And an easy way to do this is using similar triangles. Because we have a big triangle here, and we have a small triangle here. Because they have the same angles, all of them, they're similar triangles. Therefore, we can come up with a some sort of proportionality. So what we'll do is, similar triangles, we can think of the big radius 4 over the small radius r is equal to the big height over the small height. And then, of course, we can just solve this for r. which would be 2/5 h. And then since we need an r squared, we can go ahead and get this as r squared equals 4/25 h squared. And then we can import this expression in for the r squared. So this changes our volume equation into pi over 3, let's say, times 4/25 times h cubed, which we can even further combine this into 4 pi over 75 h cubed. Now we can differentiate dv dt. This is going to be 4 pi over 25, because the 3 and the 1/75 will reduce to 1/25, h squared dh dt. Now we can use information about our rate of change of volume and what the height is. So dv dt is 6. We're going to go ahead and take h equals 5. So if we do this, we'll get 25, and that 25 will cancel with that 25. So we'll be left over with 4 pi dh dt. And if we solve for dh dt, which is our goal, we will have 3 over 2 pi. And this would be meters per minute. And yeah, I do not have a decimal for that, but that is correct.